All right, hi everybody. We're going to start off today's lesson with a review from a problem that we've done quite a while ago. So when we take a look at this integral, we have x cubed plus 2x plus 3 over x minus 1. The degree of the numerator is more than the degree of the denominator. Now, what we did when we encountered this is we actually did this division. We took x cubed plus 2x plus 3 divided by x minus 1. So quick reminder on how that works. We'll put our x minus 1 out there. Our x cubed, notice there's no x squared. I'm going to put a 0x squared right there, plus 2x plus 3. And I say, okay, x times what is x cubed? That would be x squared. Then we multiply x squared times x cubed, x squared times negative 1, negative x squared. We know in long division, then we subtract. The x cubes are gone. We would have a positive 1x squared. We would drop the 2x. And we'd then say, okay, x times what is x squared? And the answer to that would be x. So then we multiply. We have x squared minus x. Now we're going to subtract again, and we're up to a 3x. Drop the plus 3. X times what is 3x? And that would be a 3. Now we're going to multiply again. Subtract one last time. We get 6. Now 6 is that remainder, and we know that we write that remainder over the divisor x minus 1. So that's just a long division. Now, because this is of the form x minus c, we also would have been able to do a substitution, synthetic division instead, where we would have laid it out here. Would have gone 1, 0, 2, 3. We would have put in a 1 there. Remember, this only works if we have a linear term in the denominator, okay, but we use synthetic division. We drop the 1. We multiply, we add, we multiply, we add, we multiply. Multiplying by 1 is so easy. We add 6. There's our remainder, and we still get the same thing. All right? Remember, we interpret this remainder, constant, x squared. All right, so then how does this help us? Well, we know then our integral is equal to x squared plus x plus 3 plus 6 over x minus 1 dx. And let's go to a new page to see how we're going to handle that. Okay, well, antiderivative of x squared. Well, that's easy. Antiderivative of x. That's easy. Antiderivative of 3. That's easy. So these three terms, okay, in fact, all of the terms before the remainder are easy antiderivatives for us. Now, here's how we handled this. We said, okay, we're going to take the integral of 6 over x minus 1. And what I'm going to do is I'm going to put the 6 out in front of the integral and write that as 1 over x minus 1 dx. So we integrated, that's why I didn't need the terms for those three, but then we still have to take the integral of this one. And here's what we need to remember. The integral of 1 over x dx is equal to the natural log of the absolute value of x. So we have, let's just get all this down again. Now we have 1 over x minus 1. We don't have 1 over x. Well, this is like the chain rule, but what's nice about this is the derivative of x minus 1 is just 1. So the antiderivative of this is the natural log of the absolute value of x minus 1 plus c. Again, if we just do a quick check on this term and we take the derivative of it, that would be equal to, well, we leave the 6 in front. Derivative of the natural log of the absolute value of x. Well, we have to use the chain rule. The derivative of the outside, derivative of the natural log is 1 over x, but we want the derivative of the outside at the inside, which is 1 over x minus 1 times the derivative of the inside, and the derivative of x minus 1 is just 1. And notice this does get us back to 6 over x minus 1. So there's review. When we had the degree of the numerator was larger than the degree of the denominator, we just divided, okay, and we were able to get a lot simpler integral to find. So then what are we going to look at today? We're going to look at a technique called partial fractions, which is going to allow us to take a quotient, a rational function, and split it up into lots of different fractions, because we're able to find the integral of that fraction, okay? Where this fraction we weren't. So we're going to be decomposing, and this is what it's going to look like, okay? When the degree of the denominator is larger than the numerator, okay, we're going to do a partial fraction decomposition. Now, I've already done this one, okay? I know that 2 over x squared minus 1, let me just double check it so I don't get it wrong for you guys, is equal to negative 1 over x plus 1 plus 1 over x plus 1. Now, if you don't believe me on that, well, let's just do a little work off to the side to check that this is really equal to that. So if I want to add these together, I know I need to get a common denominator. Oops. Mistake. That's a minus. I even looked at my paper to check and I still wrote it down wrong. That's a minus. All right, so let's see that these really are the same. Well, to get a common denominator, I need to multiply this by an x plus 1 over an x plus 1, and I need to multiply this by x minus 1 over x minus 1. Now, distributed on the top gives me a negative x plus 1 over x minus 1, x plus 1, which is x squared minus 1, plus distribute here x plus 1, and our denominator is x squared minus 1. So now we have two fractions with a common denominator. Let's add their numerators. Negative x plus x is 0. 1 plus 1 is 2. And we can see, it's supposed to be a minus, we can see that this is actually equivalent to what we had before. Now, what's the advantage to writing it out this way? Well, when I look at this integral, because we can split this up into two separate integrals, okay, in fact, let's take the negative out of this one and just put it out front. Okay. This reminds me of this right here. Okay. We know how to find that antiderivative. Okay. So this is going to be negative. What's the antiderivative of 1 over x plus 1? That's the natural log of the absolute value of x plus 1. And again, the x plus 1 we don't have to worry about because the derivative of the inside is just 1. And then this would be plus the natural log of the absolute value of x minus 1 plus c. Okay, and we have that right there. Okay. Now, depending on how much you want to do with simplifying your natural logs, using those properties that we know from pre-calculus, we can certainly do more with this. Remember that the sum is really multiplying, but actually we're subtracting that one. So if I switch the order, this would be the natural log of the absolute value of x minus 1 over x plus 1 if we wanted to show off some logarithmic properties. All right, so that's why we do this partial fraction decomposition. We take one fraction, we split it into multiple fractions, and then take our antiderivative. So what do we have to work on mostly today? We have to work on going from this to that. Okay? How do we do this partial fraction decomposition? Okay? Now, in pre-calculus, that's not something that I had time to get to. I know we get to it in college algebra, so we're going to have a little bit of learning how to do this partial fraction decomposition and combining it with our integrals. So, okay, a lot on this page to talk through. Okay. How do we do this? Well, the first thing we have to do is we have to factor the denominator. Okay. Notice on this one it was x squared minus 1. Okay. That would factor to be 2 over x plus 1 x minus 1. Okay, so first thing we do is we factor the denominator. Then each linear factor gets its own denominator with a constant numerator. So notice this became one of my denominators, and this became the other. Then part of what I said here is that each gets its own constant numerator. Now, look at the numerators here. They're constants. One is -1, one's 1. We could have ended up with 3 and -5, or 22 and -99. But the numerator is a constant, and that's what we have to solve for. We know what the denominator has to be. We're going to have to solve for the numerator. Okay? Now, if we have a quadratic, that can't be factored. Well, let me back up here just a second. So let's look at this example. We have x plus 1 over x minus 2, x minus 3. This linear factor of the denominator gets its own denominator. This linear factor of the denominator gets its own denominator. And then the numerators are some constant, and we're just going to call them a and b. And we're going to have to solve then for a, I shouldn't write plus, that would be confusing, and b. Okay, and we'll learn how to do that. Okay, so that's what happens when we have a linear factor in the denominator. Now, what happens if we also have quadratic factors in the denominator? Let's look at this example. One of the denominator's factors is linear. So it gets its own denominator with a constant numerator. But then we have this quadratic factor. Okay, it cannot be factored down anymore. X squared plus x minus 3 cannot be factored down anymore. Okay? It gets its own denominator, but now its numerator is linear. Okay? So it's got to look like the equation of a line, and we have to solve for the b and the c in this case. Now you could call those whatever you'd like. If I call this constant a, I just stick in order. I say, okay, this constant's a, this constant's b, this constant's c. Okay. Now, if we had multiple linear factors, this might be an ex plus f, but it has to be linear. It has to look like y equals mx plus b, okay, where you got your slope and your y-intercept. So quadratic denominators get linear numerators. Okay. So that's how we handle the quadratics. Now, what happens if a factor is repeated? Okay, this gets kind of interesting. Okay, so let's look at this example. We have a linear factor. Okay, that's important. I know we see the cubed here, but it's a linear factor. It's just repeated 3 times. What we do is the linear factor gets its own numerator or denominator. Then we take that linear factor squared and it gets its own denominator. And then the linear factor cubed gets its own denominator. Now, if this would have been a fourth, we would have had to have gone one more. We would have had to say d over x minus 2 to the 4th. All right, so that's how we split it up, we break them down. I'm not going to give you any like a cubic in the denominator, that can't be factored. I'm going to stick to problems with linear and quadratic factors. Linear factors get a constant numerator. Quadratic factors get a linear numerator. If it's repeated, you have to have 1 for each power up until those match. All right, so that's our introduction. In our next video, we're going to do one of these together.